Good morning, everyone. Sorry for the slight delay. Shan is having some technical issues. So one of the great characteristics of COSAC is, of course, that when we have a problem, there's a queue of wonderful people waiting to fill in. So we've done a little agenda reshuffle, and Andy Clark has very kindly agreed to swap over and go first. So Andy, for those who do not know him, has been a member of this COSAC family all the way back to about 1994. He was the recipient of the first ever COSAC award and has had a major role in creating the COSAC brand. It was Andy who was responsible for introducing people like Whitfield Diffie to COSAC. He's introduced well-regarded barristers, lockpickers, and various other hugely memorable sessions. In this case, Andy is going to talk about some work he first mentioned to me a few years ago by John Gordon, and it will be of particular interest to those in the SABSA community who've heard me reference this on SABSA training courses over the last year or two. A brilliant way to try to visualize aggregation of risk and attributes. So with no further ado, it's my great honor, in fact, to have Andy Clark open the first ever COSAC Connect. So over to you, Andy. The stage is yours, sir.
Well, thank you very much indeed, David. It's good that I got dressed early for this. I wasn't anticipating being first. And thank you for the very kind introduction. Without earlier planning, I can't actually see whether or not I'm on screen. So, David, if you can just tell me you can see me okay, that'll be fine.
I can see you clearly, Andy.
Okay, thanks. Well, obviously, I'm not with you at Killashee in person. I really wish I was. I'd like to thank the COSAC organisers for giving me the privilege of speaking at this COSAC Connect #1, and even earlier. And I realise, Sean, you're working hard in the background. I look forward to seeing your talk. I'm sure it's going to be great. Sometimes hardware is just too painful to bear. Okay, let's just walk through what I want to do in this talk. I want to introduce you to why I'm concerned about understanding dependencies, and I'm going to introduce a thing called dependency modelling. Now, some of you may have been familiar with dependency modelling before, others may not. I will try and keep this simple and straightforward, but make sure that there's enough opportunity for us to interact in the way that we would normally try and do in a COSAC environment. I'm going to use just 2 or 3 simple examples to show and illustrate dependency modeling, the last one of which will be a SABSA parallel and a SABSA example. So I think, as David mentioned at the beginning, this work, the inspiration for this, and frankly, much of the content that you'll see here, was inspired by original work by Professor John Gordon, who I'm privileged to say is a good friend of mine. He produced a paper called Keeping It Together, Dependency Modeling and Risks to the Infrastructure. Although his paper is copyright 2012, his work predates that quite substantially, and it's really innovative. John worked together with others, including Chris Baker. They've given me some help, advice, and free use of their modeling software to actually put some things together for this presentation. Now, John's paper is a seminal work. If you're interested in receiving a copy of John's paper, then there will be a poll question later in this talk. If you find this talk interesting and you want a copy of the paper, then just click on the poll and say you'd like one, and then the organisers will make sure you get one sent to you either direct by email or through a link. Now, although this book is not to do with dependency modeling, some of you may or may not have heard of it. It's called Normal Accidents. It's by a guy called Charles Perrow. It's pretty old. I think it's 1970s. And the reason I'm mentioning it is one of the things I'm particularly interested in systems engineering is the role of human behaviors. We ignore it far too much. And Perrow, I was pointed to this book when I was studying the tragic circumstances of the Boeing 737 MAX tragedies, and the inevitable, what I thought, having had some experience in that industry, of what the inevitability was of a single point failure with a single sensor. And as I was reading through some of the reports on that, which were quite illuminating, somebody made reference to this book. So I went and read it. It can be a little over repetitive, but what's fascinating for me is that Perrow highlights how human behaviors contribute to system failures. And he defines these two terms: interactive complexity. That's where two or more failures interact in an unexpected way, where nobody can really work out what's going on. And tightly coupled is when processes happen very fast and they can't be disabled or stopped. And he calls those normal accidents when those elements are present in a system. And he says that when systems have got those characteristics, an accident is inevitable. He also points out that you shouldn't confuse inevitability with frequency. I mean, the human body has high interactive complexity and tight coupling. It's inevitable that we'll die, but we'll only do it the once. So it's quite an interesting book, and I recommend you take a look if you're the sort of person that likes reading books. So I sort of encapsulate the challenge that we have in the world in which we live, because we just routinely design and build pretty complex systems, or systems of systems that have these two characteristics of interactive complexity and tight coupling. But when it gets down to that bit about assessing risk, we often have some pretty simple, crude approaches to assess risk. And it's typically something where we just have to sort of check the box at the end to show we've done it. And I do worry that risk is frequently misunderstood, and that we measure it in so many different techniques that they may or may not be credible. And in this image that we see here, I actually took this image from the back of a train that had just gone by, and I'm staggered to see these guys who are already back on the track selling their stuff. But of course, for them, the likelihood that they're going to have a problem is minimal. The train only goes past once a day, and you can hear it in the distance. So let's talk a bit about risk. Now, we've got over 600 people here. So we're not going to get a consistent definition of risk. And over the years, in workshops that I've been in, both me and colleagues, in particular, a colleague that some of you may have met at COSAC called David Porter, have collected statements that people have said as to what they mean by risk. So let me just share some with you. I rather like some of these. I like that it basically means the chance of something happening. I quite like a combination of danger and opportunity. But the point here is that there's not a clear taxonomy associated with risk that we can all understand. And often people's understanding is vague and kind of inconsistent. And that means that when we get to risk modeling, we also have a whole variety of approaches. People talk about assets, threats, vulnerabilities. They do threat prediction, loss event analysis, and so on. And then the good favorite of the red, amber, green matrices. You'll even find one in the SABSA book, page 208, figure 9.3, for those of you who have an eye for detail. And I've filled loads of these in over time, and they're kind of interesting, but then normally what we could almost define as bottom up. You know, you fill all this lot in when you've finished everything else. And then you fill this in, you check the box, and you go, well, that seems good enough. Let's just get on with what we're doing. And now that's potentially pretty problematic. And it's problematic because we're building systems of systems. So modeling risk in these interdependent systems is hard. And so we really need some decent tools to help us get through this modeling of hard problems. And we often get confused in modeling risk. And one of the things that we typically get confused about, or many people get confused about, is confusing probability and severity. And that's kind of encapsulated pretty well with this, which is the Titanic, an extraordinary ship, which, as we all know, was claimed to be unsinkable. And the thing about unsinkable ships and a claim is, well, I guess you're either unsinkable or sinkable. Partially sinkable is kind of challenging, but I find this picture rather poignant, because if you look at it, you'll see that there's not very many lifeboats, and the lifeboats that are there are actually stacked up in a way that they don't impede people's view, and that was a deliberate choice. The capacity of the ship was 2,208. They had 20 lifeboats, which was enough for about nearly 60% of the total passengers if they were filled to capacity. Now, you could kind of argue, if the ship is unsinkable, you need 0 lifeboats. But if it's sinkable, you need enough for everybody. As it turned out, the design decision that was taken was that they thought that the ship was probably semi-sinkable. And so they only needed enough lifeboats for sufficient people to be on the sea before the ship was rescued by someone else coming alongside. And we all know that that was kind of tragic. So confusing probability and severity is an easy trap to fall into. And we must perhaps try and think about putting probability and risk in perspective. So let me introduce you to Gunpowder, and in particular, this wonderful edifice. This is Rosslyn Gunpowder Mill. It's an 18th century gunpowder mill. Now, I suspect that not many of you are in the gunpowder business, so let me just tell you a little bit about it. This bit at the front is a raceway for a water wheel. Clearly in the 18th century, not a lot of electricity around, and when you're milling gunpowder, you basically have big stones that go around milling an extraordinarily hazardous substance. That happens out the back here. Out the front, the water runs down. There's a big water wheel that goes around here, and that transmits the power through into the back. You'll notice pretty solid walls, fresh out of roofs at the moment, but that happens over time. So the hard work is done out the back here, and the dangerous work is done out the back. What's interesting about it is what happens with 18th century gunpowder mills. Well, there's a simple answer. They blow up a lot. And as a result of them blowing up a lot, the insurers absolutely understood the probability with high accuracy that an 18th century gunpowder mill was going to blow up. And so as a result, they fixed the premium absolutely so that they made money. So high probability, but what they'd done is they made their profit and they reduced their risk to 0. Now, that's not quite the same as the people out the back who clearly had not the 0 risk of death. In fact, quite the reverse. So let's not confuse probability and risk. And perhaps let's take a different look at risk modeling. And I just rather like this image. I suspect that not many of you will have seen one of these before. The image on the right is actually an exploding purse. I saw this in Estonia, in Tallinn, in an hotel. Previously, a hotel that had its own central facility for the KGB. And they would routinely plant these exploding purses around the hotel in order to trap staff. Staff were told that if they found a purse or personal item, they were under no circumstances to open it. They should take it immediately to the KGB resident at the top of the hotel, unopened, and then they could return to normal duties. So if a member of staff was found to have been sprayed with purple dye that exploded out of one of these, they then went off for further training. So my view, and that of John Gordon in particular, is that risk is all about goals. And that's the fundamental principle that underpins dependency modeling. Now, by now, you may have gathered that I quite like taking photographs. My goal in this case is to take a good photograph. Now, that means I'm worried about exposure, I'm worried about composition, I'm worried about focus, and I'm pretty worried about no obstructions. Now, as one of my business colleagues, Nick Spenceley, will point out, we were standing pretty close to the edge of what is an extraordinarily deep drop here, or steep drop. This is an image taken in Anglesey in North Wales. Now, my goal is to get that image, but if I was the landowner and I was really concerned about people like Andy Clark walking around his land and taking photographs, I might be slightly more concerned about whether or not somebody might fall off. So their goal might be all about nobody falling off. So they put barriers up. Now, as a result of them putting barriers up, they've satisfied their goal and broken mine. So let's talk about goals and dependencies. So I have a goal in this case, and taking a good image, and there is a series of dependencies. Those dependencies are things like, as I said, the exposure, the focus, and so on. Now, I can't control everything about getting that image, and I can't predict all of the failures that are going to happen. So my lack of understanding about these dependencies, the less I know about dependencies, the higher my risk is going to be, because I need to understand things better to be able to understand and mitigate risk. So we need to understand dependencies better to measure and manage risk in these interdependent systems. So earlier I gave you a whole series of definitions of risk. So I'm going to suggest an alternative definition of risk, but at the first point I should give a small piece of advice, which is, if you decide to have a party outside and you build your own giant Jenga using bits of 4x2, don't be the person that knocks it over because it hurts a lot, he said, speaking from experience. So here's a revised definition of risk that I think is worthy of consideration. Not everyone will like it, but this is the one I'm going to use here. It's the degree to which the chances of achieving our goals are affected by things, the dependencies that we can't control, predict, or understand. So, welcome to the world of dependency modeling. Dependency modeling is, as it says on the slide, a method of determining risk to an enterprise using a graphical model and software that analyzes it. The origins are in assessing risk in critical national infrastructure. And what's fascinating to me is it's top-down, goal-oriented, and that immediately made me think of SABSA attributes. When John Gordon first spoke to me about this, I realized the parallels with SABSA. Now, the interesting bit is the software here does the hard work and allows what-if visualization. It uses Bayesian networks and fault mode analysis. There's the language I'm going to talk about here is John Gordon's language from his paper. The first item is a thing called a paragon. Paragon, positive goal-based entity, like a SABSA attribute. It interlinks with others underneath it that creates dependencies, and each of the paragons has at least two states, either a 1 or a 0, success or failure, okay or not okay. Dependents are paragons upon whose state depends on a superior paragon. And we have things called uncontrollables. These are paragons that have no dependencies, like battery charged okay, fuel okay, mains okay, solar backup okay. All right, so those are the three main elements. And I'll just introduce briefly the fact that within this, we can also introduce countermeasures. And so you might see things like this. We've got a threat, bad people might break in. So our paragon is no break-ins, that's the goal, and that can have a countermeasure such as either no attempts, nobody tried, or access control okay. All right, so you'll see that later on. Let me show you a simple example model. Now, please don't get hung up on these models. They are merely models, so don't try and pick holes in them. There's plenty to find, and we don't score points at the moment for doing that. Right, I and a colleague are going to go visit somebody else. We're going to go in one car. We happen to have two cars available. So for our trip to be successful, the vehicle's got to be okay. That means the car's got to be okay, one of them. There's got to be fuel available. And this paragon for industrial harmony means that there's no disruption to infrastructure. So there's no disruption to the roads. There's no disruption to the ability for fuel to be delivered and so on and so forth. Roads okay needs the weather, the traffic, and the roads to be open. Roads open is dependent on industrial harmony. People okay means that we need to be okay. We need to be healthy. Our friends need to be okay. And there's no epidemics or pandemics or lockdowns. So in this really simple model, I populate it by putting in probabilities that, for example, car one okay is going to be okay. What's the probability that car one is okay? And so on for the uncontrollables. And I end up with a picture that looks like this. This shows me that with the probabilities that I've put into my model, currently the probability of my trip being successful is 0.45. Now, again, don't get too hung up on the numbers here. Just follow through on the process. Now, I've now got a model that says this is my probability of trip successful. And I go, okay, well, I wonder what happens if I lose car one? What's the implication of losing car one? Well, the answer is not very much. The probability of my trip successful changes from 0.45 to 0.40, but I've got car two. So I can immediately see the impact of losing an uncontrollable pretty straightforwardly, just in a simple interactive way. It's clearly not the same if I lose industrial harmony, excuse me, because I get no fuel and the roads are closed. So my trip is zero, by chance of success is zero. And similarly, if there's an epidemic, then the chance of my trip successful, or the probability, is zero. So unsurprisingly, in this structure, we can look at ands and ors, and we can understand that and relationships increase risk, and or relationships generally reduce risk. So when I've got one of these graphical models, and I can look at all of the, in particular, the uncontrollables, the things that I can't influence as yet, it's really helpful for me to understand which uncontrollables have the greatest influence on the state of my overall goal. For example, trip successful. Gordon defines a series of ways of doing that, and I'm just going to share some of them now. He talks about sensitivity. I'm going to use the term influence at the moment. And so with this model in front of us, we say, okay, how much can weather okay, and uncontrollable, influence the state of trip successful? And diagrammatically, for each uncontrollable, the software draws a bar chart that represents the influence of that uncontrollable. If the bar is narrow, then it has low influence. If it's wide, it has high influence on the goal. If it's red, that illustrates the negative influence that it exerts when the uncontrollable is in a bad state, and green is positive for when it's good. And let me show you that. For example, here's weather okay. We put a number on weather okay, which is a measure of the level of influence of weather okay on trip successful. It's actually proportional to the width of the whole line, red and green. The red bit shows you the level of influence if weather okay is 0. And the green bit shows you the influence on trip successful if weather okay is 1, i.e. good. We put all of those together in a chart. And we can then see which of the uncontrollables has the greatest influence on the outcome of trip successful. In this case, we can see that weather okay at 0.504 and traffic okay have a much greater influence on trip successful than, for example, car 2 being okay, which has minimum. That's the first thing we get out of this graphical approach, is this ability to very quickly look at those things that have the maximum influence and potential impact on the achievement of our goal. The second thing that it has built within this modeling is an ability to understand failure modes. And again, I've got a simple example to show that. It's an example of pumps and tills. It's a fuel station. It's got 2 pumps and it's got 2 tills. And from an architectural standpoint, we quite like to know how to interconnect them. What's the best way to operate it? So the pump you use for filling your vehicle with fuel, and the till is where you go pay. So how do we actually wire them together? Well, we can wire them together in one of 2 ways. In simple terms, I've said, can we wire them as islands? So in this case, if you fill your vehicle with fuel at pump 1, you have to pay at till 1, and if you fill it from pump 2, you have to pay at till 2. And in the second case, you fill at pump 1 or pump 2, and you pay at till 1 or till 2. Now, the sharp-eyed amongst you will probably realize pretty quickly that actually, even though there is the same probability for all pumps and all tills, wiring them up with in functional groups makes our chances of success substantially greater. And we can see that in the failure modes analysis of this. There are 4 ways that when you're wired up as islands that you can actually fail. If pump 1 and pump 2 fail, if till 1 and pump 2, if pump 1 and till 2, and so on, don't worry too much about the detail, but the reality is there are 4 failure modes for islands, and there's 2 for functions. So pretty quickly, just by using failure mode analysis for this arrangement, we can very quickly see the better way that we can configure our systems. So that's a real rush through the fundamentals of dependency modeling. I'm now going to just take us through some of the parallels with SABSA. And I'll then move on to a simple model that I've used for a SABSA attribute. So when I mentioned that when I first heard about this from John Gordon, he said, he told me about dependency modeling, and I realized there was synergy with SABSA. It's here, absolutely. The only difference is one definition. We have a business attribute, he defined a paragon, but the 2 are fundamentally the same. So let's look at a SABSA dependency modeling example that I hope you'll be able to relate to. I'm pretty sure that for most of us, when we do modeling and SABSA modeling for people and SABSA architecture, we normally see an attribute, business attribute called available. So in this case, excuse me, hadn't had my Guinness yet. In this case, we define available as available for a data processing subsystem. So data processing available. It needs some fundamental elements. It needs sufficient CPU to be able to process. It needs, unsurprisingly, it needs data. It needs power. This particular example has a central premises with central staff, and it has remote premises with remote staff. And I've tried to put a model together that sort of reflects a little about the circumstances in which we find ourselves today, with a lot of people working remotely that previously would have worked in an office. So here's the image, here's the slide of the model. So if I can find the mouse, it's around here somewhere. So my overall paragon at the top here is data processing available. That's my goal. That's my business attribute. Here's my reference to CPU available, and that's available if I don't have a failure of the CPU, or my hot standby CPU is okay. Remember modeling the countermeasures: threat, CPU failure, countermeasure, hot standby. Similarly, data available. Data is going to be available if none of it gets lost, and there's no accidents and no sabotage. Or it's available if the data recovery is okay, either hot or warm recovery is okay. Power is available if short-term power is okay, no loss, or the UPSs are okay. Long-term power is okay if there's no long-term loss, or my generators are okay. Down here is where we're going to be focusing our efforts, but central site available is if the premises is okay, i.e. the premises is okay, or the backup central premises are okay, and my staff are okay. Central staff are normal, they're healthy, and they're not in lockdown. Similarly, for those working remotely, they're okay if the comms are okay, and we're defining that by saying the minimum number of ISPs are okay, and our VPNs are okay. And similarly, the remote staff are okay if they're healthy, and the place that they're working is okay. So I plug in some probabilities into the uncontrollables, and I get an outcome that looks like this, where my probability of success of my data processing be available is 0.63. Now, you might immediately think, wow, that's terrible. I need to be 99.9% available 99.5% of the time. Don't get hung up on that. This is measuring the probability that your system will be available at any particular time. It is not a measurement of your overall availability. This is risk, okay? So let's look at, do you remember how previously we looked at the influence that uncontrollables have on this model? Let's find a way to do that here. And we can see that there's a pretty heavy duty one here called no lockdown. No lockdown has the highest influence on the outcome of data processing available. It has a very large red component, so it can have a very substantial impact on my DP available paragon if it's bad. And also it happens to have the highest green level as well, so it can have the highest positive outcome in the event of no lockdown. So let's go back to the model. And we can see that no lockdown is here. So what can I do to improve this situation here? Well, I improve it by, sorry, I'm having to play around with the mouse here, by doing this. I've added a countermeasure for the challenge of my staff being in lockdown by putting in two bubbles. I've produced central staff exceptional, which says, in order to resolve the challenge of no lockdown and improve my overall probability of achieving my goal, I'm going to put these two bubbles together. Now let's just see what that's done. That's taken us from 0.63 to 0.74. So the impact of that is quite profound, even though the probability of bubbles 1 and bubbles 2 being okay is substantially lower than lockdown. It's made a huge difference to central available that's moved from there to there, and my overall probability of success of my paragon's gone from 0.63 to 0.74. So when we now look at good old no lockdown, we can see that we've mitigated no lockdown down to a very low level. And naturally, what we would then do is to now go forward and look at, okay, now let's look at minimum ISPs okay, VPNs okay, remote health okay, and workplace okay. So it's a really simple picture, but I've used a SABSA business attribute to illustrate that, in my view, there is a good opportunity for dependency modeling to be used in SABSA, and I think it's kind of helpful. I think it fits well. What I like is the visualization, and it means that we can work pretty efficiently. I suspect that some of you may remember the old days of risk assessment, where you filled in a bazillion questions on a questionnaire, and eventually it came out and said, congratulations, your risk profile is 42.6. And then if you wanted to find out what it was within there, you went back and answered all the questions again. Now, we're past those days, but this visualization, in my view, is extremely powerful, as is the ability to do what ifs. I've only illustrated a really small part of what dependency modeling can do. And I hope I've given you a flavor for it, but what ifs work pretty well, as does failure mode analysis. And this is really helpful. What's nice is that we can apply dependency modeling right at the start of our system architectural design to help us end up with a resilient design. I think it's worth a try, and I really hope that you think the same. So thanks very much for listening, earlier than anticipated, and I'm really happy to take Q&A. Thanks.
Thank you very much indeed, Andy, and a special thanks for jumping in 2 hours early. We have had some interesting comments going on the chat window. We have fascinating results to your polls, and we have a number of questions lined up. So everyone, please remember that you can build on these questions by producing additional comments and vote on the questions as we are discussing them. So to get us started, we have a question from Rodney Anderson over in Australia. Hello, Rodney. Hope you're well. Rodney is not able to take the stage, so I will read that out on his behalf for you, Andy. And his question is, how different is your definition of risk to the ISO 31000 definition, the effect of uncertainty on objectives? If it's different, why is it different?
Rodney, I really wish I knew the answer to that, because I don't know the definition in the ISO term to which you refer.
It was in the question, Andy. So it is the effect of uncertainty upon objectives is the definition.
Effect of uncertainty. Well, I think to a degree it's kind of parallel, although I'm just going back to dependency modeling being parallel, because dependency modeling is measuring the degree of uncertainty of those uncontrollables against our objective, which is a business attribute. So forgive me, I don't have my definition on screen at the moment. I'm playing multiple screens, so it's difficult for me to tell. So I think to answer that question, dependency modeling appears to fit neatly with addressing the definition of risk to which you've just referred, but I'd need to compare line for line with the one that I put up earlier. I hope that helps.
Thank you very much, Andy. Our next question comes from David Reed. David, I can't see you. Can you confirm that we can hear your audio? Wonderful. Thank you very much. Over to you, David.
Yeah, I was just wondering about weighting your inputs. How does that affect your dependencies? Can you negate that out, or will that have a bigger effect on the influence of lower level dependencies?
So remember that you only have to add the probabilities into your uncontrollables. Now, I said in this model that a paragon has at least 2 states, 0 or 1. Now, you can actually, in this modeling technique, you can put a range of states in there as well, and you can put probabilities of it being in each individual state. It's a much more complex arrangement. It's pretty flexible. So to answer your question, I think it's pretty practical to go and do those what-if calculations to change your probabilities on uncontrollables and see the results.
Okay,
Ask your question again. Was that all right?
Yes, that answers it.
I hope I got it. Thanks.
Thanks, David. Next up, we have Simon Cross for you. Over to you, Simon.
Morning, Simon.
Good morning, Andy. How are we doing?
Good.
Yeah, I was just wondering the practicality of doing the dependency modeling. When your organisation is changing and growing at growth, I'm sure that many of us are kind of experiencing organic growth across the cloud, and in doing that, there's loads of interdependencies that I'm kind of experiencing there. But the viability of being able to model like you described is probably hard because of the speed of change. I just wondered if you had a view on how achievable it is.
Could I ask you a question back?
Yeah, of course.
How easy is it to do that modeling with the other techniques you're using?
So we probably don't do that modeling, and I can see that there's loads of value in doing it, but really it's the how do I have the conversation with my peers to make them realize the kind of long term they should have that level of detail and be able to reference it and the value that it creates, I suppose is.
Yeah, I get the point, and forgive me for ambushing. I didn't mean to ambush you. I was just interested. I think yes, there's an opportunity here to do something quick with dependency modeling. Now we need to be careful here because, as John Gordon points out, it's very easy to produce a pretty rubbish dependency model very quickly. Mm-hmm. And there's a danger that we'll produce a dependency modeling after the event effectively to show that we've done something and justify what we've done. Its real power is if you have the ability to do top-down work. You're right, in a system and a business where you're changing very quickly, you're transferring to cloud and whatever, and your circumstances are changing, it's more challenging. But I think in line with the question I asked you, I would assert that it's probably one of the best approaches to take to deal with changing complexity, because you can actually visualize it pretty quickly. But it's certainly not a one-size-fits-all for all businesses. I guess if you're going to have to do risk modeling, I happen to find it very helpful, but it's challenging when everything's moving around you.
Yeah, I can completely see the value of it, but yeah, I get the challenges. Cool, thank you.
Yeah, it's a good question. Thanks very much.
Thanks very much indeed, Simon. Next in line, we have another COSAC regular for you. Hugh Walcott, over to you.
Hey, Hugh.
Yeah, hi, Andy. Hey, thanks for that. Really love obviously the fact that you've taken modelling to a new level with this. Now, I'm obviously interested in how you aggregate this, because risk systems become particularly large and complex. And I'm aware that you use the term influence in the supply chain of the dependencies to be able to determine your probabilities. Now, is influence an analogy to impact or potential impact? And does it take into account likelihood or not?
So, multi-part question. Let me answer that multi-part again. Firstly, I must pay credit for John Gordon here. I've presented John Gordon's work, so it's not mine. So attribution where attribution is due. Now, John actually produces a thing called sensitivity analysis. I discussed it as influence, and I'll give the real reason for that. The real reason is that I had originally put in 3-point sensitivity diagrams, and when I showed it to our chairman, David Linus, he said, I still don't get that. So I tried it 4 or 5 ways round, and he still didn't get it. So I said, right, you're making me confused as well now. I'm now going to call it influence, and I'll break it down into separate sets of diagrams. So to return to your question, Gordon's sensitivity analysis specifically does address your question. And it's a more advanced thing that I can talk about today. But yes, it does specifically address the challenges that you spoke of.
Okay, thank you.
Okay, good to see you.
Thanks very much, Hugh. Just while we're waiting on the next questioner to take the stage, I have one, Andy, but you can probably predict mine. There have been a number of chats in the chat window aligned with the work that we were talking about for SABSA, which is in the same way that you can use failure mode analysis to look at resilience to an uncontrollable, that we can use exactly the same technique to look at the point of best investment, the point of change anywhere in the dependency tree that has the most dramatic effect on the enablement of the objective at the top. Would you like to expand on that theory and how it might be used?
I would, but I'm not sure I know the answer, David, at the moment. I need to give that some thought. Sorry, it's a great question, but I genuinely don't know the answer right now.
I'm making the assertion that the answer is yes, because I've tried it.
Well, funnily enough, then it's my opinion that the answer is probably maybe, but I'll work on that.
Excellent. In that case, we can hand over to yet another COSAC regular, Mr. Rob Campbell. It's over to you, sir.
Hi, Rob.
Greetings. this is a great talk, Andy. One, because I'm currently trying to dynamically create RFI, KPIs and KRIs to determine control effectiveness across my organization. And what I'm thinking here, one of the challenges that you have is you have a control failure in one place. You rely on multiple controls, but a control failure in one place can potentially open up the organization, especially to something like ransomware. So you need to look at across the control effectiveness of multiple controls to see. So I'm wondering, have you ever used the same modeling technique to look at control effectiveness rather than risk?
Yeah, it's effectively if you think of the model that we were looking at, and you look at the control as being a paragon, and it says, the control OK, what you can do is you can deliberately fail that control, and you can look at the change that it makes on your highest level objective. So you could measure the effectiveness of a failure of each of those controls, both individually and collectively, by using the model and then doing the right-click fail this paragon.
So are you aware of anything that allows you to do it dynamically?
Sorry, say again, I missed it.
Are you aware of any tooling that would allow you to kind of measure that dynamically if you have changing values, or is it quite a static modeling technique?
It's a static modeling technique, and I'm not aware of any. In fact, if I could just amplify your question a little further, the tragedy for me is that although dependency modeling has been around for a while, and John and his colleagues wrote their software a long, long time ago, it hasn't gone anywhere. I did a Google search for dependency modeling software the other day, and it was pitifully small. I know that John is really keen that his work does go somewhere, and indeed, many of you will know an ex-colleague of mine, Vince Gallo, a few years ago. Vince actually took a lot of John's work and produced a series of plugin extensions for a tool called FreePlane, and he effectively reproduced Gordon's work in FreePlane with an idea that that would be a good vector. Unfortunately, he then got committed to other things, and I really would like John's work to continue and for a new set of software to be produced. Your question is, was it static or dynamic? The answer is pretty much static, although if John was here, he might actually say, but it's only a small matter of programming to make it dynamic. But well, I hope we can get there one day.
To be fair, actually, I've not come across anything that can even dynamically update your KPI, like a dashboard for KPIs, effectively on control effectiveness. So it's something that I'm trying to build out and work on just now. So it's an interesting concept, and I'd love to extend it to include that systemic control failure and the impact change, because certainly with ransomware and the changing landscape, if you have any sort of a control change or you drop below your acceptable threshold, you want to be confident that your other controls are still going to potentially help with the issue. So yeah.
So I guess if you do the what if analysis, that at least gives you an a priori view as to what might happen.
Thanks.
Thanks very much, Rob. Andy, we have a question from Miroslav Kiss on a no stage, so he can't take the stage. I'll read it out on his behalf. It says, an interesting systematic approach, but dealing with complex systems, hundreds of software and hardware components, I/O, and millions of lines of code with vulnerabilities, attacks by malware. How long would it take to model risk for such a complex system?
Well, I'll give you a lawyer's answer. It depends. And I guess that's because we have to put probabilities in for uncontrollables. So in complex systems, we're going to have a lot of paragons. Now, the depth of those, the depths of the tree below a top-level paragon, and a paragon might be software okay. So I've got millions and millions of lines of code. So software okay might break down into the relevant components being okay, and those again go down into their own subcomponents. So it's straightforward to build a small model quickly and then build out from it. But at some point, you're going to have an assessment of the probability of those uncontrollables being in one or other or more states. Now, this technique is not going to let you model failure rates or easily model failure rates in millions of lines of code. This is more looking at the enterprise side. I'm sure there is an approach that you can use. I've not done it, to look at how you might measure the probability of success in software. I've never tried it. It's an interesting question, but yeah, for big complex models, this technique is actually very powerful, because what you can end up with is potentially an uncontrollable that is the output of a previous system. I don't want to go into that in too much detail at the moment. And in fact, that's the sort of question I would ask someone who's very familiar with driving this software, because what they have told me is it's very easy to get sidetracked and produce a bad model easily. And in fact, some of the best models happen once you've built the model once, seen the errors of your ways, thrown it away and started again. So it's a good question. For big systems, I'm sure it's challenging, but I do believe this has a role.
Okay, thank you very much. We have a question from Rashid Al-Madani, again with a no stage request. I think you answered the question in your presentation, but perhaps you could reiterate for us, how do you calculate the overall probability of achieving a goal, provided that the probability of all of the subdependencies are set?
That's just done through the standard probability and Bayesian calculations in the tool.
Okay, there's a number of...
Or as John Gordon might say, magic.
Magic. We have a number of comments going through the thread about tooling. Do you have a suggestion that you'd like to get a group together to look at that possibility?
Sorry, of tuning?
Tooling. I said that.
Tooling.
You heard it in Brighton, sorry.
Yes. Divided by a common dialect. When I first postulated this idea, which was at COSAC in Melbourne, maybe a year ago or maybe two, I don't recall. No, a year ago. I said that I would be very happy to help coordinate a group of people getting together to produce tooling. And indeed, that was the discussion I'd had with Vince when he looked at extending FreePlane. The difficulty of that is that a lot of people say they'd like to help, and then very few of them step up at the end, or frankly, we've got a day job to do. I would be very happy to help in this instance. I really would. And if people are interested, genuinely interested, and have the time to do it, let's do it. I think it would be good to do it somehow through the SABSA Institute or whatever, and I'll leave that to you and your colleagues to decide how you'd like to instrument that. But I'm happy to be there.
Okay, thanks very much, Andy. I have used that or been influenced by your introduction to that work in a number of ways in developing the next generation SABSA foundation training, both in multi-tiered attributes dependency, domain modeling, and various other aspects. So I would be extremely happy to see a SABSA Institute working group on that, and I'll get back to you out of band about how we get the people who are prepared to do some work as opposed to just talk about doing some work. I'll talk to you about that out of band. So thank you very much, Andy. A brilliant start to our conference. Shan will forgive me for saying, as the longest standing presenter in COSAC history, you probably deserve to go first anyway. But thank you very much for filling in a couple of hours early.
No problem. I'll see everybody in the social networking later, and I'm around all day.
Okay, so just to reiterate, if you missed it, if you look at the poll question, you can request a copy of John Gordon's paper through the poll. Thanks very much indeed, Andy. We're going to move on to our second session with Chris Blunt, and he will be with you very shortly.